Hi folks. Today for our applications of differential calculus, we're looking at something called related rates. So it's when two or more variables experience change in relation to, it's typically time, but it doesn't have to be time, and they can be connected by an equation. So as a real simple first example, let's think about, imagine this is a ladder leaning against the side of a house, and I start pulling the bottom out like this. If I know how fast I'm pulling the bottom out, I should have some idea of how fast the top is descending. And if I think about it in some moment, so let's say we freeze it right here. Okay, we've got certain dimensions. We've got a height, we could call it y. We've got a width, we could call it x. There'd be the ladder connecting them up. And the rate at which x is changing, the rate at which I'm pulling it out, is the change in x with respect to time. Rate of change. Similarly, y is going to have a rate of change, and that's going to be called dy by dt. In other words, they're the derivatives of x and y with respect to time. Before we actually do any related rates questions, let's just refresh our memories on implicit differentiation. Up to now, we've always been differentiating with respect to the independent variable. So essentially, we've been doing this, the derivative with respect to x. The derivative of x with respect to x is just 1. Whereas we know from implicit differentiation, the derivative of y with respect to x, if you differentiate a y, you get a y prime. But this notation is really not accurate enough now that we're going to be differentiating with respect to a bunch of different variables. So instead of calling it y prime, let's stop being lazy. We'll actually call it dy by dx. If you differentiate with respect to x, x behaves nicely. This becomes 2x, whereas y squared is going to become 2y times what we might have called y prime, but now let's put it in that nice Leibniz notation, dy by dx. If you had some other variable like r, this is going to become 3r squared, and make sure that you tack on your derivative on the end. Things are going to be pretty similar if we differentiate with respect to time. So here we're looking for the derivative with respect to time. But in this case, all of the variables behave like y or r did over here. Even for an x, the derivative of x with respect to time is 1 dx by dt. Okay? Or just, probably we want to say dx by dt. The derivative of y with respect to time is going to be dy by dt. The derivative of x squared will be 2x times that derivative tacked on to the end. This one's going to turn into 2y dy by dt from the chain rule, and this one's going to turn into 3r squared. So I guess the takeaway is that even x has to have that derivative tacked on to the end if we're differentiating with respect to time. We'll do 3 examples today, but before we go there, let's take a look at some steps for solving these types of problems. So in general, if you have a word problem, which these will mostly be, you want to draw a picture. You want to define your variables and their derivatives. And the derivatives are the rates of change, which might be told to you. And when we talk about derivatives, they're the derivative of something with respect to time. So I'm going to use my favorite just general variable, a poorly drawn unicorn. Derivative of whatever with respect to time. After we've defined what we know, we're going to make an equation. Don't sub any values yet. Next, you're going to differentiate with respect to time. And when you do that, don't forget to tack on those derivatives. To tack on derivative of whatever we're talking about with respect to time. Don't forget about implicit differentiation, essentially. And finally, we'll be able to solve for the unknown. Now that we have a method, Let's use it to answer a related rates question. So we're imagining a pebble that's dropped into a calm pool of water and it causes circular ripples. And each ripple moves outward at 1 foot per second. What rate is the total area increasing when the radius is 5 feet? So there's a lot to unpack there. Let's try and draw a picture. Here's the pebble. It falls into the calm pool of water. And the ripples go outward. And at a certain instant, you've got a radius of 5 feet. Rather than having to imagine this whole thing, let's take a look at a demo. Here we've got a lovely picture of what happens when a drop of water hits a calm pool. Let's try it out in video form with a pebble. There it hits the bottom. You can notice that it rolls a little bit up and to the side. But you can also see the ripples coming outward. And they come out in a circular fashion. And that circle is going to be defined by its radius. The radius itself is going to be changing size. It's moving outward at a uniform rate, and that rate is called dr by dt, the change in radius with respect to time. The question we have is, how does that affect how area is changing, the area that has been, quote, rippled over time? Now that we've seen what it looks like, maybe we can add more information to our diagram. So each ripple moves outward at a rate of 1 foot per second. What rate is the total area increasing at when the radius is 5 feet? So at this instant, the radius is 5 feet, but it's also getting bigger. This right here is a rate of change, and it's the rate of change of radius. So that is dr by dt. And we know it to be 1 foot per second. And we call it positive because the quantity r, the radius, is increasing. What we want to know is what rate the total area is increasing when the radius is 5 feet. So we want to know a rate of change of area. In other words, we'd like to know dA by dt. So as this moves out, it's more and more area that is affected by the ripple. And you could argue that if this happens in an ocean, then it goes out and affects the whole world. Okay, so we need to now make an equation that connects area and radius. Ooh, I know one of those. The area of a circle is pi r squared. Now, does that equation have any derivatives in it? No, because we haven't differentiated yet. Now, we're going to differentiate with respect to time. And it's important that we do not sub our r in yet. That happens later. Because if we subbed it in, then we just have a constant here, and of course its derivative would be 0. Both area and radius are changing, so we need to actually differentiate and then sub in. If I differentiate with respect to time, so diff with respect to time, a becomes dA by dt. Pi r squared, well, this 2 is going to come down front. I'll get 2 pi r. And then I have to use the chain rule, and it's going to be times dr by dt. Now some of you are going to want to write that as r prime. Please don't. Please be specific about what the rate of change is. Now we're ready to actually sub in our values. So dA by dt is unknown. That's what we want to find out. 2 pi r is 5 feet. I'm going to include the units here. dr by dt is 1 foot per second. And if I work this out, I'm going to get, well, 2 times 5 is 10, so 10 pi. Foot times foot is feet squared per second. In other words, I have a rate of change of area per time, or per second. We could write that in decimal form as about 31.4. So in that instant, when the radius is 5 feet, then area is increasing at this rate, 31.4 feet squared per second. And as soon as that instant's over, then it's going to be at a different rate. As a final answer, we can say the radius is increasing at a rate of 31.4 feet squared per second in the instant when the radius is 5 feet. We put our units into the equation. You don't need to. You can do it just with the numbers. So over here you could have said just 2 pi times 5, and you would have got 10 pi. But the notation would actually help you out anyways. It's telling you it's area per time, so it's going to be feet squared per second. Let's try another one. For our next example, we're going to investigate that case that we looked at the start of the lesson. If you have some kind of ladder leaning against a wall and you start to pull away its base, then it has a rate of change for its bottom, or its horizontal, and a rate of change for the top, or its vertical rate of change. And those two things should be connected to each other. I guess the question is just how. So we've got a 25-foot ladder. It leans against a wall. The base is being pulled away at a rate of 2 feet per second. How fast is the top moving down the wall when the base is 15 feet from the wall? Again, that's a lot to decode. So let's make just a basic little diagram. We've got a ladder. Maybe I'm drawing it like this, straight-ish. Okay, and it leans against a wall. And the bottom is 15 feet out from the base of the wall. So we could say that x is 15 feet. Now I'm going to use x for my horizontals, and then I'm going to use y for my vertical. That's something that they told us. They also told us that the ladder itself is 15 feet long. I'm going to call that z, 25 feet. And there are some other things I could figure out. I could figure out how high it is up the wall. The other piece of information that's given to us, though, is this rate of change. It's being pulled away from the wall at a rate of 2 feet per second. That is a rate of change in the horizontal, or an x. Now, as you pull it out, x would increase. It would get bigger and bigger. So that means that its derivative is positive. If the derivative is positive, it means the original quantity is increasing, as long as we take the original quantity to mean a length. Okay. So dx by dt is 2 feet per second. Z we've got right here. Y we don't know. dy by dt. So we know that this is going out from the wall, and it's also sliding down. dy by dt is actually what we want. There's another sneaky piece of information that's in there. The ladder itself is not changing size at all. So because it's not changing size, its derivative would be 0 feet per second. Now we have two unknowns. That's not a great position to be in. It's better than having a bajillion unknowns. But we don't know y or dy by dt. So we're going to make an equation here. And the equation we could make is just Pythagorean Theorem. X squared plus y squared would equal z squared. Before we differentiate, let's see if we can easily find out anything else about this. I think we can easily figure out what y is. Okay? Straight from Pythagorean Theorem, this is not any differential stuff or derivative stuff. If I just sub in 15 for x, 25 for z, run this through, that's 225, this is 625, you'll get that y is 20. We can figure that out before doing any work or doing any differential work. All right, so now we've got how high it is up the wall, how far it is, and how long the ladder is. We've got a nice equation. We haven't subbed anything into the equation that we're going to differentiate yet. Now we're ready to actually differentiate with respect to time. So let's do that. X squared is going to turn into 2x by dx by dt. Y squared will turn into 2y dy by dt. And z squared will turn into 2z dz by dt. One thing you might notice after you differentiate is that there are all these 2's, so we could divide each side by 2. That'll keep it balanced. You don't have to, but it looks a little slicker. We'd have x by dx by dt plus y by dy by dt equals z by dz by dt. There's a nice differentiated version of this Pythagorean equation. Now we can sub. So I know that x is 15. I could do this with the units, but I'm just going to go with the numbers for now. 15 dx by dt is 2. Y is known to be 20. Dy by dt is unknown. In fact, it's what we're looking for. Z is 25. And dz by dt is known to be 0. So in other words, we get 30 plus 20 dy by dt equals 0. I can solve that for dy by dt. I'll just move the 30 over. And divide by 20. I'm going to put it in decimal form, but you can leave it in fraction. Doesn't matter. So 30 divided by 20 is going to give me 1.5, and it's negative. What are the units going to be? They're going to be straight from the Leibniz notation here. Y is a length. It's measured in feet. T is a time. It's measured in seconds in this question. Lovely. That's dy by dt. That's the numerical answer to our question. Let's make sure we actually answer it in words, though. So it says, how fast is the top moving down the wall when the base is 15 feet from the wall? What this derivative means is that the length y is decreasing, and it's decreasing because dy by dt is negative at a rate of 1.5 feet per second. So the negative gives us whether the quantity is increasing or decreasing, and this is the rate that it's happening at. If we answer the question as it's asked, it says, how fast is the top moving down the wall when the base is 15 feet from the wall? The top is moving down the wall at a rate of 1.5 feet per second. And that's true when the base is 15 feet from the wall. All this stuff is in flux. So if these quantities change, if the rates change, then that's going to affect dy by dt. But for this instance, this is the correct answer. Here's our last question for today. You're standing a quarter kilometer from a railroad crossing perpendicular to the railroad. So here's you, here's the railroad. The train goes by at 80 kilometers an hour. At what rate is the distance between you and the train changing when the train has traveled a half kilometer down the track from the railroad crossing? So before we even draw this, which is supposed to be step one, let's just be clear that this is a length. It's going to be an x or a y or a z. This is a length. It's going to be an x or a y or a z. This over here is a rate of change. That is going to be a derivative. Then depending on how we draw our diagram, it's either going to be dx by dt or dy by dt. Let's make a drawing and see which one it's going to be. So here comes the railroad track. Somewhere down here is the train, and we're standing right over here, and there's a quarter kilometer and a half kilometer. We'd be better off looking at a demonstration.
Chugga 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 choo choo. Chugga 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 choo choo. Chugga 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 choo choo. Chugga chugga choo.
Move over, Michael Bay. There is a new master of special effects in town.
So this is the instant that we actually care about. It's when the train is a half kilometer down the track and you're a quarter kilometer from the railroad crossing. Notice that the train itself is moving forward. So from that we can tell that dx by dt is 80 kilometers per hour. You, on the other hand, are not moving at all, so dy by dt is going to be 0 kilometers per hour. The thing that we want to find out is what is dz by dt. In other words, what is the rate of change of the distance between you and the train?
So hopefully now this diagram makes a little more sense. X is increasing at a rate of 80 kilometers per hour. Y is not changing at all. X is a half kilometer down the track. Y is a quarter kilometer from the railroad crossing. Z and dz by dt are unknown. We want to know what the rate of change is. So in the end, this is what we want. dz by dt. We want. I would say that anytime you know 2 out of the 3 sides in a right-angled triangle, it's worth your time to go and find the last side. We'll probably need it at some point. So to do that, I'm going to do it on my little scrap board over here because it doesn't relate to differentiation at all. So I have x squared plus y squared equals z squared. So that's a half squared plus a quarter squared equals z squared. Okay, so that would be a quarter plus a 16th is z squared. Z squared would be 5/16. Or if I simplified here, I'm going to get z is the square root of this. Now I'm doing all of these as x, y, and z are just lengths. They don't have directionality applied to them. Maybe sometime later on you'll do some vector calculus. You'll want to have some directions applied to these. But for now, let's just say they're lengths. So I only care about the positive square root here, which would be root 5 over square root of 16 is 4. There's the exact value. If you want to find it as a decimal approximation, it's 0.559. But it's just lovely, like this, root 5 over 4. What I like about this setup now is that there's only one unknown, the thing that I'm looking for. Okay, so that leads us to reviewing our steps. We made a picture, plus we acted it out. We defined variables and derivatives, and acting it out can be really helpful. Anyways, back to the task at hand. Define variables and derivatives. Yep, we're going to make an equation. And that equation is just going to be any equation that connects these variables. Their derivatives will be connected once we differentiate. So let's do that. Differentiate with respect to time is going to give us 2x by dx by dt, 2y times dy by dt, and 2z by dz by dt. I don't like these pesky 2's, so I'm going to divide both sides of the equation by 2. It doesn't affect your answer, though. You can leave them in there. Okay, let's sub in what we know. X by dx is going to be a half times 80. Y is a quarter. dy by dt is 0. Z is root 5 over 4. And dz by dt is unknown. It's what we're looking for. It would be the rate of change of this length z, which is the actual distance between you and the train. So that gives me 40 equals root 5 over 4 dz by dt. Times by 4, I get 160. Divide by root 5. I get the exact value of this. So there is a perfect representation of the rate of change between you and the train itself. The distance is increasing because dz by dt is positive at a rate of 160 over root 5 kilometers per hour. But that's kind of difficult to think about, like how big is that number? So we can head to the calculator and we'll find out that this is 71.6. And the units are going to be whatever z is in, which is kilometers. Should have put it over here. All the lengths are in kilometers. And all the times are in hours. The last piece of the puzzle is actually answering the question, and we should probably do it in a sentence. At what rate is the distance between you and the train changing? So let's see. As the train's going down the track, it should be that the distance between you is increasing. Positive derivative says yes, z is increasing. Out of context, this is saying the length z is increasing at a rate of 71.6 kilometers per hour. In context, what it's saying is the distance between you and the train is increasing at a rate of 71.6 kilometers per hour. Anytime we're talking about a derivative, we're talking about a rate of change. Now, just to be clear, that's in the instant when the train is a half kilometer down the track. Once that instant's over, once it's, say, 1 kilometer down the track, this rate will no longer be valid. It's always in flux. You might notice that in all the triangle questions we did today, or in both of them, that one of the sides was not changing. When we come back to this on our next day on related rates, we'll have ones where all the sides are changing, and we'll also invoke trigonometry as well. Good luck with the practice, and let me know if you have questions.